Now let's put our efforts into trying to make this game more dynamic. There's nothing much going on here, of course. There is just we're just generating a collider, and there is just the ability for us to move our platform around. And as you can see, because I changed the aspect ratio, one thing I just noticed is that the limits are wrong. Okay, so this is something that we need to pay attention in the future, because we can generate the limits dynamically as well, using a similar approach as we did for the scenario limits. But we won't deal with this now, because it's not something that's really important for the project to work as expected. But instead, we're going to work on the apple movement. We're going to make the apple move in a such way that when it, for instance, hits one of these corners, the movement gets reflected, and then it goes this way, and then it goes this way, and then it goes this way, and so on and so forth. Okay, so this is what we're going to focus on this video. So what we're looking for the movement, we want to start with two directions for the movement, two possible directions. One is going to be the direction going this way, and as you can see, this is a vector that has components 1, 1, or something that goes along this direction. So it can be an alpha value that multiplies this direction, so it can be something that's bigger, it can be something that's smaller, so on and so forth. But it's going, as long as alpha is positive, it's going to be something that lies within this line here. Okay, and the other possible direction is going to be this one, which is of course -1 and 1. So what we're going to do, we're going to randomize a number, and depending on the result we get, we're going to start with this vector or this vector. So let's say that we can generate a floating point value that has its limits between -1 and 1. And then we're gonna get, let's say, a value that's -0.3, or maybe 0.1, maybe 0, and then we can just use a function that's going to get the sign of this number, and the sign will basically be -1 or 1. So this function is going to give -1 for this value, it's going to give 1 for this value, and it's going to be 1 for 0 as well. So this is a very simple approach, and we're going to do this right now. So going back to Unity, I'm going to create a new script. I'm going to call it Apple. Double click to open it up on Model Develop, so we can start coding this. Alright, so first of all, we need to have a velocity for this movement. So I'm going to define a public floating point value here, which will be the velocity. And to start with, whenever I apply this script to an object, I want this velocity to be 1 as a standard value. So I just say that this is going to be equal 1. So whenever I apply this script to a game object, the velocity will start out being 1. And on the start function, I'm going to define a direction, but I need this direction to be a member of the class, so I can have access to this variable on any function that I may want. So I'm going to define a private vector3 underscore direction. This is a common way to write private members. We just do a underscore in front of the variable. And so we can pick a random direction. We're going to define this float value, and this is a random value. And to get a random value that's between two limits, we can use the function random.range. And this asks for a minimum value and a maximum value. So we're going to basically randomize between min and max. And this has two overloads. It has one that takes integers, and here is a quick description. So returns a random integer number between min inclusive and max exclusive. So if you say the minimum is 1 and the max is 2, it's going to return either -1, 0, or 1. The maximum is not included. But instead we're going to use the floating point approach. So this includes both minimum and maximum. It's going to return a floating point value. and we're going to say -1f just to make sure that we grab the floating point overload, and 1f. If we take off these f's here, we're going to use that integer overload, which is not something that we're looking for. You can also put a 0.0 here just to make it even clearer that we're using the floating point overload. And now the x component will just be the sign of this floating point value. So mathf, which is the class that holds all sorts of mathematical functions, and inside this function we have these sign operations. So it's going to return the sign of this floating point value. And the floating point value, of course, is the random value. And now for the direction of the movement, we can just assign a new vector to this one. And the x component is, of course, this integer that we've just defined, so x component. The y is always going to be 1 because we always want to move upwards to start with. And the z is going to be 0 because there's no movement on the z component. This is a 2D game. And just so we grab a vector that is normalized, and what does that mean? Is that we want a vector that has size 1. We're going to do direction.normalize. We're going to call a method that is going to normalize this vector here. Note that this is different than direction.normalized. This attribute is going to return the normalized version of this vector. So if we use this approach instead, we would need to assign the normalized vector to the direction again. But if we use this method, direction.normalize, this is going to normalize this vector and it's not going to return a normalized version. Now we have a normalized vector, and in other words, a normalized vector is basically a vector divided by its length. And what this is going to do, it's going to make such operation that the length of this vector from now on is going to be 1. So now the size of this vector is going to be defined by the velocity. So if we get the velocity being equal to 1, we get just a normalized vector because anything times 1 is anything. If we multiply it by 2, we get a direction that's twice as big, therefore we get a velocity that's twice as big, so on and so forth. And now what we want to do in the update function is just to grab the position of this element, and we can do get component transform dot position plus equals, that's basically adding to the position. So doing plus equals is just doing equals itself plus the direction times the velocity. I'm just gonna put this into parentheses so we make sure we're first multiplying direction times velocity and then we're adding this to the position. So doing that times equals is the same thing as doing this. We are adding to the position instead of assigning to the position. And this works with minus, with multiplication, it works with division, and all sorts of operations. Also, please note that there's a shortcut for writing get component angle brackets transform. We can use just transform with a lowercase t instead. So transform the position plus equals direction times velocity. This is a shortcut that's not available for any sorts of components, but the transform component is kind of surviving through the versions of Unity. So you can just use this shortcut to access the transform component of the object where this script is attached to. You don't have to write get component transform all the time. And let's see what this is going to do. So we can go back to Unity. And when I hit play, oops, there's an error here. It says cannot implicitly convert type float to integer. And that's because the sign function returns a float, but I'm trying to assign this to an integer. So I can just convert the result of this to an integer, or I can use a float instead. It doesn't really matter. I can just use float x component equal to the sign function, or I can say this is an integer, and I can force the returning value to be an integer by doing parenthesis int in front of this function call. This is going to make such an operation that the returning value is going to be converted into an integer before it gets assigned to this local variable. So both of these solve the problem. Now the error is gone. So when I hit play, first of all, of course, I need to apply this script to the apple. So I'm just gonna click on the component to hide them because my screen is broken and I can't see much. So I'm gonna assign the apple here. There is just a velocity, so we're good with 1 for now. So it goes this way. When I hit play again, it goes the other way. And now we have a randomized initial direction, okay? Of course, we need to multiply the movement by time.delta time. So this movement is not dependent on the frames per second of our application. And now we can increase the velocity to make the movement faster. 10 looks a bit too much, maybe 5. Yeah, that looks good. And you just saw that when I hit the collider here, it tries to get through. Eventually it's gonna go through because I'm forcing it by adding to the position, and this is not something that we should do when we're dealing with physics. But we just want to hit this wall, and then this invisible wall, right? And then we're gonna grab its normal, which you'll learn within a few moments what it is. But we just need to hit this wall, and we're gonna reflect the movement direction, okay? So we won't be forcing the position to keep adding to itself, so we won't pass through this invisible wall, okay? But as you can see, the physics is working, and we're colliding with that wall. All right, so now how do we reflect such movement? Okay, so let's go back to drawing a little bit. And as you can see, let's say that we start out with a direction of 1 and 1. So we're going to move our apple, and eventually it will collide with this wall. Okay, so you gotta note that when you collide with something, you can access a component that's the normal of the element that you just collided with. And the normal is something that it's orthogonal to whatever you collide with. In this case, this edge has a direction vector that points this way, and something that's orthogonal to this one will be something that points down, or maybe up, but in this case it's going to be down. So what we want to do is basically we want to grab this direction, which is something that it's going to be pointing this way, and we want to reflect this vector along the normal that's represented by this sign. And after we do that, we're gonna end up with a direction that points this way. So we basically just reflected the movement, and eventually, of course, we'll be moving down this direction. We're gonna hit this wall. This wall is going to have a normal that points this way because it's orthogonal to the edge. And we're going to reflect, so it's going to be something like this. And we're going to be going down towards this part of our scenario, which of course is a game over, but we'll try to reflect the movement with the platform. But for now, let's just do this reflection thing. So I can open up my script, and for that we need a function that actually detects collision, and Unity has a built-in function for that, which is called onCollisionEnter. And this is just like start and update, which are functions that are called by Unity when something happens, when a special event happens. So to get access to this function, we need to type in void onCollisionEnter 2D, because we basically are dealing with 2D collisions. If you're dealing with 3D collisions, we just need to take off this 2D here. So in this case, it's 2D. And the parameter of this function is collision 2D collider. So what's going to happen here? Whenever the apple collides with something, this function is going to be called, and whatever something we collided with is going to be passed through this parameter called collider. So through this parameter, we can have access to what collided with the apple and a lot of information of the collision, such as the normal. And let's just type collider here so we can have access to its members. And as you can see, we have the collider here, we have the game object that just collided with the apple, and we have this contacts variable. And this is the places where any sort of contact occurred. And this is also a vector. And anytime we have a collision, we know that we have at least one contact point, because if we collided with something, we might have one contact point. So if I access the index 0 of this, which I just proved that will always exist, I can have the normal here. And this is what we're looking for. So we basically want to reflect the direction along this normal. So we can just access the vector3.reflect method. And here it asks for a direction, something that's going to be reflected, which is of course our direction, and the normal. And the normal is just the normal of the contact point. But of course, this is going to return the reflected vector, so we need to reassign this to our direction. And this is pretty much it. So I'm just going to normalize the direction again, just to make sure that we always have a normalized vector. And this should do it. So let's go back to Unity. Let's try it out. There you go. That looks wonderful. Let's see if it works with our platform. It does not, because we don't have a collider in our platform. So if you just go to our lives bush, component, physics 2D, add a box collider here. I'm just gonna expand our collider so we can see the gizmos. And you can see that it wraps up our geometry perfectly. And if I hit play, not our geometry, right, but our sprite, because we're not dealing with a 3D thing. And it just works beautifully. Okay, one more step of our game is done.